Assalamualaikum and good morning. Today our group will present project assignment. This is our group. So my name is Siti Nurlena binti Azmi. I will go to introduction. This project involved the design and simulation of the low pass filter with a 3 GHz cutoff and band pass filter with a 320 MHz bandwidth. Using advanced design system ADS, the filter were initially developed using LUM element theory, then transformed into practical transmission line model using reshaped transformation and Kuroda identity. To ensure the design were physically reasonable at microwave frequency, the MSUB model was defined in ADS. These include key parameters such as dielectric constant, substrate height, and conductor thickness. The value allow accurate simulation of microstrip behavior. Overall, the project demonstrates how theoretical filter design can be efficiently implemented using modern tools, bringing the gap between academic knowledge and real-world RF and microwave engineering.
Okay, so I will explain about low pass filter. A low pass filter is a filter that passes signals with a frequency lower than a selected cutoff frequency and attenuates signals with frequency higher than the cutoff frequency. The exact frequency response of the filter depends on the filter design. The filter is sometimes called a high cut filter or treble cut filter in audio applications. A low pass filter is the complement of a high pass filter. For the application is removing high frequency noise in audio signals, smoothing data signals, anti-aliasing in digital sampling systems, and filtering out unwanted frequencies in communication systems. And then I will explain about band pass filter. The definition of the band pass filter is a circuit which permits the signals to flow among two particular frequencies, although divides these signals at other frequencies. These filters are available in different types. Some of the BPF band pass filter design can be done with an external power as well as active components, such as integrated circuits, transistors, which are named as an active band pass filter. Similarly, some of the filters use any kind of power source as well as passive components like capacitors and inductors, which are named as a passive band pass filter. For the application the first one is communication systems, isolating frequency bands. Secondly is audio processing, enhancing or isolating sound frequencies. Third is medical filtering ECG or EEG signals. And lastly is optical systems, filtering light wavelengths.
The loop element model, also called loop parameter model or loop component model, is a simple representation of a physical system or circuit that assumes all components are concentrated at a single point and their behavior can be described by idealized mathematical model. The loop element model simplifies the system or circuit behavior description into a topology. Kuroda identity in RF and microwave engineering are a set of transformations used to convert over or irrealizable loop element circuit, particularly those with a series stub, into more practical design using transmission line. Rigid design theory in RF and microwave technique primarily revolves around matching impedance using reactive element to minimize signal reflection and maximize power transfer.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Aina Akila binti Burhanuddin, and today I will explain to you for part design and result for low pass filter for equation task 1. Okay, for task 1 question is 3 GHz cut off frequency, 41 dB at 8.7 GHz, 3 dB equal ripple. And from the specification, we can get the cut-off frequency, which is 3 GHz. Insertion loss is 41 at 8.7 GHz. And for ripple, it's 3 dB. And for the frequency, we can conclude that frequency is 8.7 GHz. And for omega, we use this equation to get the omega, which is 54.66 gigahertz. And next for omega cutoff, we can get 18.85 gigahertz. And from this omega, we can get the 1.9 for normalized frequency. As you can see from the graph, we can conclude that insertion loss is at 41 dB at here, and then we the normalized frequency we get 1.9 dB, which is at here. And from the graph, we can get the n equal to 4, which is 4 order filter. And next, for 3 dB ripple that we get before, which is our n is 4, the G1, G2, G3 and G4, we use this. And for the calculation, we calculate the C1, L2, C3 and L4. And for L1, we can get 3.649 picofarad. For L2, we can get 1.985 nanohenry. For C3, we can get 4.612 picofarad. And for L4, we can get 1.570 nanohenry. Next, from the calculation that we get from the graph, we put in the simulation in the circuit from the calculation that we get. And from this simulation, we can get the graph, which is low pass filter. And for M1, we get from the 8.7 gigahertz frequency, and for M2, we get from 3 gigahertz frequency. Okay, next, from the our circuit before, we transform it into Richard transformation. And from the circuit, the L, we change it into a short circuit, and for the capacitor we turn into open circuit. And then we can get this circuit from the Richard transformation based on the low pass filter lump design. And for this is for our inductor, and this is for capacitor, which is for open circuit. So for the open circuit, we will have to divide the G2 and G1 and G3, which is to get this number. Next, for Kuroda identity, from the Richard transformation before, we change it into the series circuit. And for this one, it was a case 1, which is a shunt stub followed by transmission lines. And we will get Z1 equal 1, Z2 equal to 0.291, and we will get 1.291. And then for the short circuit, we will get 0.225. And from the low pass filter implementation, we can get this circuit turn into the Kuroda identity, into the series implementation. And from this series transformation, we have to calculate the N2 for series transformation using this equation. From this equation, we will get this normalized impedance for different stub. For the Kuroda identity, we transform into a normalized impedance and denormalize with 50 ohm impedance for different stub. And for the normalized impedance, the calculation before we put at the circuit. This is for Z1 and 2, and this is for Z2 and 2. And for the denormalized, we have to multiply with 15 ohm to get this the result for the denormalized impedance. So after we multiply with 50, we will get this last circuit for denormalized. And then we put the number to the low pass filter implementation for the last circuit.
Okay, so this is the design and the result of band pass filter. Firstly, we need to list out the center frequency, bandwidth, equal ripple, and N. So the center frequency is 3 GHz. For the bandwidth is 320 MHz. For the equal ripple is 0.5 dB, and for N is 5. So for the lower cut-off frequency is 3 GHz minus with 320 MHz divided by 2. So the answer is 2.84 GHz. For the upper cut-off frequency is 3 GHz plus 320 MHz divided by 2. So the answer is 3.16 GHz. So the other one is the picture of the N equals to 5. So this is the result. Okay, so I will explain about the omega naught, omega 1, omega 2, and then delta. So the answer for the omega naught is 18.85 GHz, and then for the omega 1 is 17.84 GHz, for omega 2 is 19.85 GHz, and for delta is 0.1066. We calculate G1 until G5 based on our result on the N equals to 5, and then for the 0.5 dB for ripple. So for G1 equals to 1.7058. So L1 equals to 165.76 picohertz. And then for C1, the answer is 16.98 picofarad. So for G2 equals to 1.2296. So for answer for the L2 is equals to 30.60 nanohertz. And for C2 is equals to 0.0920 picofarad. So for the G3 equals to 2.5408. So the answer for L3 is equals to 111.29 picohertz, and for the C3 is equals to 25.29 picofarad. So for the C4, for the G4 equals to 1.2296. So for the L4 is the answer is 30.60 nanohertz. And then for the C4 is the answer is 0.0920 picofarad. And then for the G5 is equals to 1.7058. So the answer for L5 is equals to 165.76 picohertz. And then finally the last answer is for the C5 is equals to 16.98 picofarad. From this slide, you can see the result from ADS. I designed it for the S param. I started with 1 GHz and I stopped it at 6 GHz. For the step is equals to 0.01 GHz. So the output we get the band pass filter. So for the M1, the frequency is negative 0.485, and for the M2 is equals to negative 0.116.
Next, I will present this part. After we construct a low pass filter with M-sub. So for the M-sub, the specification already given in the report. So this is a circuit for the low pass filter. We use 5 M-lin, 4 M-log, and 4 M-T. The value for M-lin, we take the value from microfabrication on the upper part, and for M-log, we take microfabrication value from the lower part. So for the M-T value, we take from M-lin and M-log value. This is a circuit before we tune, and this is a circuit after we tune. So this is a graph before we tune. As we can see, the M1, we got the 3 GHz and the frequency is 13.744. And for the M2, we got at 0.700 gigahertz, and the frequency we got negative 27.854. After we tune the graph, we got M1 is a 3 gigahertz and the frequency is negative 3.386, and for the M2 we got at 8.7 and the frequency we got negative 41.471. This is a tuning that we already tuned the graph, and this is the value and we got.
Okay, for the conclusion. In conclusion, filter theory and design form the backbone of signal processing and communication systems. Lump element filters are suited for low-frequency applications, while distributed element filters excel in high-frequency domains. Techniques like the Richard transform, Kuroda identities, and equal-ripple designs help achieve optimal frequency selectivity while addressing practical challenges like component tolerances and insertion loss. A systematic approach, such as the insertion loss technique, enables engineers to design filters that maintain signal integrity and system efficiency across modern technologies.